Hi everybody. In this video, we're going to start looking at different aspects of water and how those different aspects will impact our embalming process. If we look at the properties of water, one of the things is that it is a very good solvent. In fact, it's called the universal solvent. They call it that because most things will dissolve into water over time, even solids, things like that. It is an amphoteric substance. Amphoteric means it can act as both an acid or a base. One of the things when we talk about making salts, for instance, salts are created through a neutralization reaction between an acid or a base, acid and a base, I should say. But usually how they define that is an acid or a base other than water, because what comes out when you make a salt in a neutralization reaction is a salt and water. Water is very stable. It's mainly due to the hydrogen bonds. The same thing with its surface tension. It has a very high surface tension because of the hydrogen bonds. If you remember, surface tension is the force acting on the surface of a liquid to minimize its surface area. Water has a very high surface tension. It also has a very high heat of vaporization. Again, heat of vaporization is the energy needed to change 1 gram of liquid to gas at boiling point. Remember, boiling point is the temperature at which a liquid will start to boil. Heat of vaporization is the energy needed. And so when you heat water up to boil it, it will hit the boiling temperature, which is 212 Fahrenheit or 100 degrees Celsius. But you have to keep adding heat and keep adding heat and keep adding heat to break up all those hydrogen bonds. And that lag in time is what makes steam much more dangerous than just boiling water. So those are some of the properties of water. We're going to next look at an aspect called water hardness or hard water. When they talk about hardness of water, what they mean is there's minerals and metallic ions dissolved in that water. Now it could be numerous different things, but the ones that really that are common and that concern us would be calcium and magnesium. The calcium is the one that we really take notice of. One of the problems with water hardness is that it destroys the action of soap. If you've ever tried to take a shower in water hardness, you always feel kind of grimy afterwards because the soap didn't really do what it was supposed to do. And so you get kind of this film feeling almost on top of you. There are 2 different types of water hardness. There's temporary water hardness, and this is caused by bicarbonate salts of calcium and magnesium. This is calcium bicarbonate. This is magnesium bicarbonate. The bicarbonate is HCO3, and there's 2 of those. That's why they call it bi. HCO3 is carbonate. HCO3 parentheses 2 is bicarbonate. So this is calcium carbonate. This is magnesium carbonate. You find that in temporary water hardness. And you have permanent water hardness, which is made up of chloride and sulfate salts of calcium and magnesium. You'd have, there we go, calcium chloride here, and this is magnesium sulfate. Again, the magnesium we don't really concern ourselves with too much. That doesn't concern us so much. What concerns us is the calcium. So how do we get rid of water hardness? Well, temporary water hardness can be done through boiling. As you boil this temporary water hardness, that's going to render the bicarbonate salts insoluble. So when we say insoluble, it's no longer being dissolved by water, and it will just kind of fall out, oftentimes in little clumps. And so this is kind of the process of it. You've got calcium bicarbonate here, and it's soluble. So if you had a glass full of temporarily hard water, it has this calcium bicarbonate floating around in it, but you can't see it because it's dissolved. But as I heat it, as I boil it, it's going to become calcium carbonate, not calcium bicarbonate, but calcium carbonate, and that is insoluble. That will come out as like little chunks. They will what's called precipitate. See if I can spell that out. Precipitate. It's really hard to draw with this. Boop, boop. Okay, so precipitate means when something was soluble, it becomes insoluble. And oftentimes when it becomes insoluble, it solidifies, and so it falls out of the solution. That's precipitation. So boiling this temporary hard water will make this soluble calcium bicarbonate turn into insoluble calcium carbonate. You'll also get water and CO2 out of that. To get rid of permanent hard water, you can do a few different things. It can be removed by adding sodium carbonate, this Na2CO3. This is the reaction for that. So we have the calcium chloride, the chloride salt of calcium salt that makes permanent water hardness. You've got the sodium carbonate here, and what you'll get out of this is calcium carbonate and salt, table salt, NaCl. Again, this is a metathesis reaction because they're going to switch partners. Okay, so this chlorine is going to go to the sodium. This carbonate's going to go to the calcium. We can also remove permanent water hardness by adding soap. Again, this is one of the reasons why taking a shower or a bath in permanent hard water, the soap will inactivate and remove the minerals from the water. The problem is that by doing that, it inactivates the soap, and so the soap doesn't do what it's supposed to do. And the last way you can do it is ion exchange. This is how water softeners work. You replace the hard water calcium ions with soft water sodium ions. And this is kind of how that works. You have the calcium chloride in the hard water, you have the sodium, and out is going to come NaCl2 and calcium. And that's why we fill up our water softeners with salt, with sodium salts. Now, why we even talk about water hardness is because hard water can have an effect on our embalming. If we don't do something to remove the water hardness, the calcium ions in the hard water can cause the blood to clot. And when you die, most of the blood goes into your capillaries, about 60 to 70% goes into your capillaries. And if it starts to coagulate in the capillaries, you're not going to be able to push it out so that you can get diffusion. So you'd get probably really good distribution, but no diffusion, which means no embalming. So one of the ways that we do this is we use anticoagulants. Wrong. There we go. Coagulants. A lot of people think that anticoagulants are designed to bust up clots, and they're not. Anticoagulants are there to soften the water, because you might not know if you have water hardness in your funeral home, because if you do and you try to pump that in the body, you're going to have a real hard time getting the blood out. Okay, so that's the water hardness effect on embalming. Next up are hydrates. You've probably run into hydrates before, you just might not know it. Hydrates are chemicals that form a union with water to form a crystal. So it's some substance that interacts with water and creates a matrix that creates this crystal. And crystals are just basically rocks. This is an example of a hydrate. Now you'll know a hydrate because of this dot here. So this is copper sulfate. That dot means that it's a hydrate and that it's holding water in this matrix. That's what's made this crystal. Okay? That's how you know a hydrate is that dot. It just means it's holding water in a matrix. Now, because these substances are interacting with water, they have what's called the water of hydration, or sometimes called the water of crystallization. That's just the water held in chemical union with the hydrate. Now, because it's in there and it's not really chemically combining with it, it's just kind of being held in a matrix, you can also take that water back out technically, and that's when you would make an anhydrous hydrate. Anhydrous hydrates are hydrates that have had the water of hydration removed, and that's technically called a dehydration process. And you can have some hydrates that are partially hydrated and some that are completely anhydrous. Now, hydrates can go through decomposition and synthesis reactions. So a decomposition reaction of a hydrate is like any decomposition reaction, one reactant, two products. In this case, we have a hydrated copper sulfate hydrate. If we add heat to that, then we would get the anhydrous copper sulfate. So this one has been hydrated, we heat it, the copper sulfate loses its water of hydration, and you get these water molecules come out. That's a decomposition reaction for a hydrate. A synthesis reaction is what we're probably more familiar with. That's when we have two reactants and one product. And for a hydrate, it's going to be the hydrate and water. So this would be an example. So this is a partially hydrated hydrate. That's actually plaster of Paris. Plaster of Paris is a powder, and you add it to water. So plaster of Paris plus water is going to give you gypsum. Gypsum is this calcium sulfate's hydrated form, if you will. And gypsum is solidified plaster of Paris. Now, we actually use plaster of Paris in funeral service. You can use it for restorative art purposes, but you have to protect tissue from it because it can suck the moisture from the tissue. But you can use it as a dehydrant to suck moisture out of, to purposely suck moisture out of tissues that might be swollen or edematous. Now, there are two major types of hydrates. There are hygroscopic and efflorescent hydrates. Hygroscopic hydrates, or hydrophilic meaning loves water, will attract additional water from their surroundings. So this would be like plaster of Paris. This would be cement. That's how you go from powdered cement to solidified concrete, is you add water. And hygroscopic hydrates will oftentimes keep sucking up water from their surroundings. Concrete does that. And so will plaster of Paris. That's one of the reasons why we don't use plaster of Paris necessarily on a lot of restorative techniques, because if it touches tissue, it's going to suck moisture out of that tissue. The tissue will desiccate and kind of shrink, and then you end up with gaps between the tissue and the plaster of Paris itself. Again, that's also the reason why we use plaster of Paris to dehydrate tissue. So really edematous tissue. I've used plaster of Paris bandages to wrap around that edematous tissue. It forms like a cast, basically, but it's sucking the moisture out of that tissue. Now, there is a certain type of hygroscopic hydrate that will suck in so much water that it dissolves itself, and that's called a deliquescent hydrate. You can buy these in the store, these deliquescent hydrates. They're used for wet basements. It's a little bucket, and if you shake it, it sounds like there's rocks in there. You open it up, punch holes in the top, keep it in your basement. It sucks the moisture from its surroundings to the point where it actually dissolves itself. You go back a month later, let's say, and there's going to be a lot less rocks in there, if any at all, depending on how wet your basement is. But that's a deliquescent hydrate. We actually use these in funeral service as mold inhibitors for ship outs. We used to use a little powder. We put it in a petri dish, drill holes in the top of the petri dish, put that the foot end of the shipping container or the casket, and any moisture that was going to form on that body would get sucked into that deliquescent hydrate, and it wouldn't make a mess because it would just dissolve itself. And that's kind of handy when you're doing ship outs. The other type of hydrate is called an efflorescent hydrate. We don't deal with those really. Efflorescent hydrates are kind of the opposite. They will give off water of hydration to the surroundings. So we don't really have any use for those. It's the hygroscopic hydrates and the deliquescent hydrates that we have use of. The last thing we're going to cover in this video is hydrolysis. Hydrolysis, you're going to hear a lot about. It's one of the major steps in decomposition. Hydrolysis' definition is cleavage with water. What they mean by that is that hydrolysis is going to break down polymers. Polymers are large chains of things. And so, for instance, in embalming, it's what we're concerning ourselves with is mainly proteins. Proteins are polymers of amino acids. And so hydrolysis comes in and splits those apart, starts to break the chains apart. They also call it cleavage with water because the water molecule itself is going to split. And I'll kind of depict that here in a minute. This is technically a double replacement reaction when it happens. So for instance, see if I can draw it out here. Let's say that each of these links is an amino acid in a protein. Okay, well, water would come in, H2O, comes in and it splits apart. Now, when water splits apart, it's always going to split apart into a hydrogen proton, so H+, and a hydroxide ion, hydroxide anion, OH. And in proteins, the way they're structured, this will split. And so we'll just kind of go bloop, take that one out. It splits apart. Now you've got two sets of amino acids. And the OH would go to that one, and the hydrogen would go to this one. Okay, so double replacement. This part went over here, this part went over here. Now, usually the products of hydrolysis end up being acids and bases, and it's kind of an odd thing is that you'll have a strong acid and a weak base. Again, why we concern ourselves with hydrolysis is that it is the most important factor in the initiation of decomposition. Hydrolysis is going to come in and start to break down large biochemical chains. Everything in your body is a polymer. Proteins are polymers, lipids are polymers, carbohydrates are polymers. Hydrolysis is going to come in and start to break those down. So we are going to try to slow that as best we can. Again, one of the things that formaldehyde is really good at is dehydration. So the more water we can get out of the body, the less decomposition is going to happen. You're going to see hydrolysis quite a bit throughout this semester. So that finishes it for this video. Next, we're going to look at solutions.